So we've seen that we can use a shorthand notation to represent all of the linear combinations of a finite number of vectors, right? If we have m vectors, the span of v1 all the way up to vm would be all of the linear combinations we can build from these m vectors. There's a few other things we've seen. The span of the zero vector is the zero vector, right? Because if I build any linear combinations from the zero vector and I add any sort of coefficient in front of it, I'm always going to get zero. So that's the only thing I can really get as a linear combination if I start with zero. If I have a vector which is not the zero vector, the span of that one vector is going to be a line through the origin along V in whatever space V resides. And in R2 and R3, if you had two vectors which were not zero, and such that, one of the vector was not in the span of the other, so it wasn't a linear combination of the other, it wasn't a multiple of the other, then the span of the two vectors is a plane through the origin. So if U is not in the span of V, it means that the two vectors don't lie on the same line. And when you do all of the linear combinations from these two vectors, you get a plane. Just as one of these vectors was Bank Street, the other one was Laurier. The span of all of these would be all of the locations in the downtown core that are at ground level. Plane. There are some odd things about spans, though. And we've mentioned them, like the two spanning sets can have a different number of vectors and span the same subspace. So spanning sets are not unique. But there's another way in which they are not unique. You can have the exact same number of vectors in both spanning set, and they will span the same set. Now we saw an example, right? We had two spanning sets that had two vectors each. The span of both of these pairs of vectors was the same in both cases. Here's another example. There's one each. Spanning set is 1, 2, and 2, 4. These are parallel vectors. They represent the same direction in R2. And so their spans have to be the same. All linear combinations of the vector 1, 2 are scalar multiples of 1, 2. And all linear combinations of 2, 4 are scalar multiples of 2, 4. And each scalar multiple of 1, 2 is also a scalar multiple of 2, 4. Just the multiple is half as much, right? So they span the same line, even though the spanning sets themselves are different. There's another example here. If I look at the vectors 1, 0, 1, 0, 1, 0, that's one spanning set. If I look at the vectors 1, 1, 1, 1 minus 1, 1, that's another spanning set. Both of these spanning sets span subspaces of R3 because each of the vectors in R3. Is it clear, though, that they actually span the same subspace? How would you prove that? You would show, for instance, that every vector in one of the spanning sets is in the span of the other spanning set, so that you can write the vector 1, 1, 1, for instance, as a linear combination of 1, 0, 1, 0, 1, 0. That shows that 1, 1, 1 is in the subspace W. It's a very simple linear combination. And 1 minus 1, 1, you can also write it as a linear combination of the vectors 1, 0, 1, and 0, 1, 0. So that vector here is also in W. So we use the big theorem on spans, and that tells us that the span of the second spanning set is contained in W. And so in particular, that the spanning set, which is called U, is contained inside of W. And you do it the other way around. You pick the two vectors in the spanning set for the first set, you showed that you can write them as linear combinations of the other ones, and hence that W is also contained in U, and you don't have a choice. Both of those are the same spanning set. The non-uniqueness is maximal, right? Every vector space except for the zero vector space, has infinitely many spanning sets. So you can find tons of ways, infinitely many ways, to find vectors that will, when you do linear combinations, give you the subspace in question. You can't help this. That's just the nature of spans and spanning sets. But it's not a real problem. It's just an inconvenience, but it's not a real problem. There's a second issue which is a little bit more serious, but this one is one that we can fix. If you look at the number of vectors in a spanning set, it doesn't really tell you anything about the size of the span, the size of the space of linear combinations from these vectors. For instance, the span of 1, 2 is exactly the same thing as the span of 0, 0 and 1, 2, and the span of 1, 2, 2, 4, and 3, 6. Even though the first spanning set is one vector, the second one is two vectors, the third one is three vectors, they all end up spanning the same subspace. It's not too hard. The second inequality, the 0, 0, doesn't really change anything, right? Because if you're doing linear combinations of the 0 vector and the 1, 2 vector, then you're going to have A times 0, 0 plus B times 1, 2. And it doesn't matter what A is, because that contribution right here is always going to be the 0 vector. And that doesn't add anything to this combination. So it's pretty easy to show that the span of 0, 0, 1, 2 is exactly the same thing as the span of 1, 2. For the second equality, you could rewrite the third span as, well, a set of linear combinations, right? Combinations of 1, 2, 2, 4, 3, 6. There's a different parameter in front of each of them, A, B, and C. And you can take out a common factor of 2 from the second vector and a common factor of 3 from the third vector. And what you end up with here is that every linear combination of 1, 2, 2, 4, and 3, 6 is in fact just a rescaling of 1, 2. It's a linear combination of 1, 2. So that set is obviously a subset of the span of 1, 2, because it only contains linear combinations of 1, 2. The reverse inclusion also holds. It's very not difficult. Give me any t and r, then t times 1, 2, which is a linear combination of 1, 2, is also a linear combination of 1, 2, 2, 4, and 3, 6. All I need is to have as my coefficient for 1, 2 in here be exactly the same as the t that's here, and the other coefficients would be 0, and the full sum then gives me exactly the same thing. So the span of both of these spanning sets is the same. They span the same subspace, which happens to be a line, because this thing here is a line through the origin in R2.